All right, in part 3 here, we are going to be going over vertical shifts and horizontal shifts of these trig functions, sine and cosine. Vertical shift is a pretty easy one, and it goes along with just when we want to vertical shift any function, we just add or subtract a constant onto the end of it, right? No matter what our function is, if we add something onto the end of it or subtract something onto the end of it, we're going to shift that graph up and down because we're just changing the output of the function by a constant. So here we go. If we want to add a value onto the end of it, or I guess technically subtract it, we can move our graph up and down. So here's an example of cosine of theta plus 2. That's the blue graph that's shown up here. It's been moved up 2 units, so we can see how its midline is now up here, right? Instead of being along the x-axis down here, that midline is moved up 2 units and it's oscillating around that. So when we do vertical shifts, there are a few aspects of our graph that we have to really keep in mind. The amplitude and the relationship to the scaling on our axes, right? Because now this is just a standard cosine curve, so it only has an amplitude of 1, but if we shift that graph up by moving that midline, if we have a different amplitude, we just need to make sure the scaling along the y-axis can sort of accommodate that. So just sort of in summary, essentially, if we add a positive value, it's going to move up. If we add a negative, right, a value that's less than 0, we're going to move it down. So if we wanted to do an equation where we moved this same function but move it down, we could do something like y equals cosine theta minus 3, right? That would shift it down 3 units. Pretty simple idea. We could also have x as our variable instead of theta. I just went with theta because that's what we had there before. All right, let's go ahead and clear this. Move forward. So here we have a couple graphs. So the red one that we have here is our basic y equals sine of x. You can see it's got our single cycle of sine going here from 0 to 2 pi. And we kind of want to examine what the equations of these other graphs might look like. I'm going to do that by looking at how the midline has moved, where that's moved. So here is our midline for this blue graph. We've moved up exactly 3 units from what I can tell. So this would be y equals sine x plus 3. And it still has a period of 2 pi. We can kind of compare it here, right? We're at 0 still, and we end a cycle at 2 pi. So we're still having the same period. So there's no b value that's in place. Our amplitude is still 1. We're still only going 1 above the midline and 1 below the midline. So no other transformations. The only thing that's going on here is that vertical shift. So that's all we need to do to change that equation. Similarly, we have this green graph. So we have one cycle right here, again going from 0 over to 2 pi. So that's one cycle, standard period. The only thing that's different about this curve is that we moved it down. We moved it down 2. So y equals sine x minus 2. Again, so the only things that were going on here with these graphs were a couple vertical shifts. We could do more. We can do amplitudes, we can do reflections, we can do changing the period, we can mix all this stuff together, but right now we're keeping it somewhat simple. All right, so let's make it a little more complicated here. So we have a equation, y equals 3 times cosine of x minus 4. I already got the questions here for you of what's actually happening to it. So we have an amplitude of 3. We're going to be moving up 3 and down 3 when we oscillate from the midline. And we also have a vertical shift of 4. So we're going to go 4 units down. Again, that's going to change the midline. Usually we have our midline right there along the x-axis at this place right here. But we're going to actually move it down to be at -4 instead. Small change, but it does make a difference. Something that I like to do in these cases is taking into account our amplitude. I do like to sort of figure out where the maximum values are going to be and where the minimum values are going to be, because those happen in relation to our midline. So being our amplitude of 3, we're going to be going 3 units above and 3 units below this midline. So we're going to be going up to -1 at a maximum value, and we're going to be going down to -7. I like setting these upper and lower bounds just to remind myself that I do have an amplitude and kind of where those maximum minimum values will occur. From there, we can actually just start graphing our 5 points because the scaling is actually already done for us here. And we even have it from 0 to 2 pi, again, because this is going to have a period of 2 pi. There's no number here in front of x, no b value in front of x to modify that period. It's a 1, I guess, technically, so 2 pi over 1. So anyway, our 5 points for cosine are that we're going to start at the maximum, we're going to end at the maximum. In the middle, at pi, we're going to be down at our minimum, and then we'll be at our midline, which is down here, at these quarter points, the 1/4 and the 3/4. And so then we can kind of sketch our curve. It got really wonky on me on that second half, but there we go. That's our single period of cosine with our maximum values, our minimum value, and our midline values. It's not too difficult. Again, we're only putting a couple things together at a time here. We can really kind of do much more than this. We can do all of these transformations at once, and it starts to get a little more complex, but we'll build up to that. Okay. Yeah, I already did this. Okay, so phase shift. Phase shift is our last transformation that we're going to talk about. So phase shift is when we move our graph left or right along the x-axis. Phase shifts are when we subtract a constant, or technically we could add, because we could do something where we, let's just give an example where we subtract a negative value, like -pi/4. Remember that subtracting a negative is really the same thing as adding. So it could be plus in here as well. And we'll kind of talk about which of these moves left and which of these moves right. Hopefully remember from our basic function stuff that if you subtract a value here, you're going to move to the right. And if you add a value, you move to the left. It's kind of counterintuitive, right? Because we think about subtraction as being negative and negative left, but with these horizontal shifts, it actually is a bit backwards. And when we add, we actually move to the right instead. We move to the left instead of the right. Again, these horizontal shifts are a bit counterintuitive, and we have to always sort of keep that in mind. So again, if this C value is positive, which means you're subtracting a positive number, you're going to be moving to the right. And if the C value is negative, which means you're subtracting a negative, which means you actually add it, you move to the left. And honestly, that's confusing, but the process of actually implementing this on the graph and how it changes our x-axis scaling, this is the hardest transformation. We're going to be spending a lot of time, especially if we have kind of weird shifts that aren't exactly a quarter or a half of a cycle. They can get really challenging. And so this is going to be one of the hardest ones. We're going to spend a ton of time with this scaling along the x-axis. That's where it really starts to get intricate. All right, so here we have this purple graph, which is our basic sine curve. Again, I can sort of outline that. We have one period taking place here. Go back to that, sorry. Our purple graph, so it goes from 0 all the way over to 2 pi, does one cycle in there. And then we have this black graph. This black graph's been sort of shifted. It's just a little bit off. If we take that purple graph and we move it over to the left a little bit, we get that black graph, right? All the points are just kind of moved over just a little bit to the left. And it looks like if we kind of examine the scaling on the axis, we're moving to the left pi/4. So left pi/4. That's the amount that we are moving it. This is a sine graph. So when we go to write this equation, it'll be y equals the sine of, in parentheses, x plus pi/4. Remember, plus moves us to the left, which is counterintuitive. Again, we think plus, positive, right? That's not. Plus, when we're talking about a horizontal shift, is to the left. Okay. Some people like to think about it as moving the axes to the right. If we, instead of shifting the graph, we think about shifting the axes, the coordinate system behind it moves to the right, but that's kind of a weird way. So anyway, that's our equation. That's what's happening. And we can see that all of the points, again, are just moving over pi over 4. They're moving over pi over 4. And you can kind of compare each point as being just pi over 4 to the left of where that standard sine curve was. All right. So here we go. Let's look at this one. We have a cosine graph, y equals 2 times cosine of x minus pi over 2. So we have an amplitude of 2. And we have a phase shift, a horizontal shift that is going to move us to the right pi over 2. Let's talk about what this means when we're creating our own graph. What this means is that instead of starting at 0, where we're used to beginning, we're going to be starting pi over 2 to the right of that. I have to kind of think about what that means. Pi over 2 to the right. Okay. I don't know exactly where that's going to be, but we'll kind of think about it. And pi over 2 is a pretty standard angle, right? Usually when we do our standard scaling, looks something like this. This is our standard scaling for a period of 2 pi, and we go from 0 to 2 pi, great, whatever. Well, in this case, pi over 2 is actually a pretty easy phase shift to implement. Pi over 2 means that we're actually going to be beginning here. Sorry, we're doing a cosine curve, so we're not going to be beginning right there. We're actually going to be beginning at a maximum value there, but we're going to begin at this place. That's where we're going to kind of start our single cycle. And our cycle length needs to be 2 pi. So if we start at pi over 2, we can't end here. We need to go a little bit further past that. So what I like to do, obviously our period here is 2 pi because we're not changing the period with this one. So our period is 2 pi. I need to figure out where it is that I'm going to be ending. This is relatively easy. I mean, we moved over pi over 2, so we just need to go one more section here. But let's actually kind of figure that value out. Let's figure out what the coordinates of that value would be. We take our starting point and we add our period to. That should give us our ending point. Starting point plus the period, that's going to be where we end. So let's go ahead and do that. So pi over 2 plus 2 pi. 2 pi is the same thing as 4 pi over 2. So getting us with a common denominator, 4 pi over 2. Adding those two things together, we get 5 pi over 2. That is our ending point, 5 pi over 2. Okay, and now what's sort of in the middle of that? What's exactly in between? We can see that again on this graph. We can actually already see that this is going to be exactly in the middle of it. But if we weren't sure of where that exact middle point was, if maybe that wasn't already given to us with a nice standard scaling, we could actually average the beginning and the end for ourselves. We could take these two things and average them. Add two things together, divide by 2. So that would be 6 pi over 2 divided by 2, which is 3 pi over 2. And we can see, well, that is the exact value that we end up there. Again, this is a little more important when it's trickier to see, but I'm kind of talking through what needs to go on. And again, since our standard scaling already even gives us these quarter points, there's no need to figure these out either. But well, I could if I didn't have them for myself, I could also figure out this middle point too by, again, just averaging these. Take those together, pi over 2 plus 3 pi over 2, divide that by 2. That's 4 pi over 2, which is 2 pi divided by 2. There you go. We end up with pi. We can figure these out by averaging them. And that's a strategy that we will implement moving forward. We will be averaging these to sort of figure out these quarter points. But anyway, we kind of have everything figured out that we're gonna need at least along the x-axis. We feel good. We're gonna have a full cycle here, beginning, middle, end, quarter points. So we have our x scaling. The only thing left for us is now our y scaling, and that has to do with the amplitude and if we had any vertical shifts, but we don't. So an amplitude of 2 means that we're going to be going up to a maximum of 2 and down to a minimum of -2. So there we go. Cosine, we're graphing a cosine curve. Cosine starts at maximum, again, starting at pi over 2 because of that shift. Ending here is also at maximum. In the middle, we're at our minimum point. And then we have our quarter points, our 1/4 and our 3/4. Those are our 5 points that we need to graph this. So we'll just go ahead and plot this. One of my better graphs the whole time. Pretty smooth curve. So anyway, we have shifted over here, pi over 2 to the right. We have an amplitude of 2. We've marked all of our scaling appropriate here along the axis, and not too bad. So anytime we have a shift of a quadrantal angle like this, like pi over 2, pi, 3 pi over 2, 2 pi, it's not going to be too bad. These are going to be pretty reasonable. It's when we start having some weirder ones that we're going to look at in a minute that this really starts to get intricate. Let's go ahead and clear what we have. All right, so here's a hard one. So let's take a peek at it, see kind of what's going on. So we have a reflection. There's a negative here. So this is going to be a reflected sine curve. So that looks, just to remind us, so this is sine, but now instead of going up, we go down and then up. So this is our reflected sine curve. That's just keeping that in mind in terms of where the 5 points go for the reflected sine curve. And then also we have a shift to the left plus 2 pi over 3. So we're going to go to the left 2 pi over 3. I also like to read that as 2/3 pi. So I'm going to scale this. I have to kind of think about what scaling to use here. I have 2/3 of pi. That is a unit circle angle. That's like, whatever, 120 degrees, 2/3 pi. I'm going to count my scaling of as 1/3, just so I can kind of even things up. So this will be 1/3, 2/3. So 1/3 pi, 2/3 pi. So we're going to be starting here, and sine does actually start on the axis. Sorry, these are negative values too. I don't know exactly that this is the way I want it to look. I'm kind of rough drafting my x-axis and seeing if how this looks and everything. I don't, again, I'm not exactly sure that this is the precise way that I'm going to end up having my axis look, but I'm kind of setting up a rough draft for myself to see if, I can make some changes from here. All right, so we have our starting point set. Now we need to figure out where the ending point is going to be. So this function will have a period of 2 pi. There's no b value, so there's no b, no multiplier for x. So we take our starting point, 2 pi over 3, and we add a full cycle, which is 2 pi. Again, common denominator, that becomes 6 pi over 3. 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. 8/3 pi. Okay, so I'm going to be ending at 8/3 pi. So I need to go back and fix the mistake I made. Perhaps you didn't see it, but I left off a negative. We actually are starting at -2/3 pi. Big mistake there. That does affect this answer here, obviously, right? That's going to give us 4/3 pi. I was a little bit caught off guard with my answer, which is why I started thinking about it, but 4/3 pi. So again, I'm starting at a negative value. I need to keep that in mind when I added that. So ending at 4/3 pi. Let's go ahead and keep scaling the way that we were. So 4/3. So this would be, we're counting by 1/3. So this would be 1/3, 2/3, 3/3, 4/3. This is 4/3 pi. So 1/3 pi, 2/3 pi, and 3/3 pi, which is, remember, just pi. So we're going to be ending right there. Okay, we know where we're starting, we know where we're ending, and I've counted a nice even increment. So that's something, right? I've counted nice even increments. I'm counting by 1/3 of pi on my axis. Now I need to know three more points, 3 more places along my x-axis. I need to know the middle. I need to know what's exactly in the middle between these. So I could average these two numbers. That would be one thing. In this case, I actually think I might be able to kind of just count increments over 1, 2, 3, 1, 2, 3. Yeah, this right here is my middle, 1/3 pi, positive 1/3 pi. So I could do it that way and just sort of, since I did create nice even scaling, I'm counting by the same thing here. I could have found it that way, but let's pretend that that was not obvious to us or something, or we just didn't see it. We could find this number in a different way. We can average these endpoints. So negative 2/3 pi plus 4/3 pi. Add those together, we get, oh, sorry, and divide by 2. Add those together, we get 2/3 pi, because we have negative plus positive here. Divide by 2. 2 divided by 2 is 1. We end up with pi over 3. So, yep, we found it the same way. That's our middle of our cycle. I'm going to go ahead and erase that stuff up here. Again, I'm just sort of using this to figure some stuff out. And then I need to know my quarter points. So I need to sort of figure out, I have my beginning and my middle. My quarter point should be somewhere in between these. So I know it's going to be like right in here, right? Well, that's a little bit off, right here. I just don't know what this number is. It should be kind of exactly between 0 and negative 1/3 pi, or the middle between these things. I can kind of go either way with that. I'm just going to average these 2 points. I'm going to average these 2 points to figure it out. So again, that's negative 2 pi over 3 plus pi over 3 divided by 2. So here, I add these together, I actually get negative pi over 3 divided by 2, which is negative pi over 6. Okay, negative pi over 6. That's my 1/4 point here. Kind of just averaging things out. Let's go ahead and do this again to figure out this other one, right? We need to figure out what's in between, what's the third 3/4 point over here, right? We know it's in this region, but let's just figure it out. We're averaging pi over 3 and 4 pi over 3. That's 5 pi over 3. When I add those together, divided by 2, that's 5 pi over 6. So 5 pi over 6. I need these scaling I need this scaling present just so I know exactly where these maximum minimum values are. Okay, I'm going to try to erase some writing on here that's not really necessary for us. So let's go ahead and erase this. Now I have some scaling that I'm at least moderately satisfied with. I'm saying this one is a hard one. I'm doing a lot of stuff here that may not be necessary for most problems, but I'm trying to talk through how I come up with my answers. Okay. Now, we didn't scale the y-axis at all, but this is a regular sine curve. There's no amplitude. Amplitude is just 1, so we're going to be going up to 1, down to -1. We've already graphed 3 of our points. We know the beginning point, we know the middle point, and we know the ending point, right? So we've already graphed these 3 places for our sine curve. So we're missing our minimum and our maximum. So we have a minimum here at negative pi over 6. We just figured out that that was our quarter point for negative pi over 6. And we have a maximum point right here, 5 pi over 6. So that's our sine curve. Some pretty messy scaling here, but I have all the important numbers marked. I have my beginning, my middle, my end, and my quarters all marked, and they're all in, roughly appropriate regions here. I don't have anything that's like totally unclear about where it is. I counted nice and even scaling. Those are some of the places that we can really get off. So let's go ahead and sketch in that curve. Again, this one was pretty difficult. I think a scaling of something like this is pretty nasty. And it wasn't horrible to do it. All right, let's go ahead and clear this. All right, so putting it all together, we can have all of these transformations show up at the same time if we want. Usually they don't all show up at the same time. Usually we're going to have a few, but we could end up with an equation that looks sort of as complicated as this, where we have some sort of an amplitude that's not 1. We could even have a negative value here that caused it to reflect. We could have a number here for B that changes our period, have a phase shift of some sort and a vertical shift, right? Some parts here that I do want to draw your attention to is in particular this part in the brackets. Let me just like kind of highlight what I'm talking about. We're going to get more into this in 3.2, but this part right here is pretty important. The B value that is the multiplier for X, right? If we distribute this in, right, it would be B times X. That's what affects our period. And this here is our phase shift. In order for us to really know both what the period affecting value is and what the phase shift, we will have to factor it in this format. So if I have an equation that is something like this, just making something up here, it's 2x minus pi. I need to factor that 2 out, because right now, if I'm just looking at it, I may be deceived to think that I'm having a shift to the right of pi, but that's actually not the case. I do need to make sure this is factored out. So I have to look at this expression and factor this 2 out of it. So it becomes 2 times x minus pi over 2. So that when I redistribute this in, it's the same thing as that, right? And when I redistribute this, 2 times x, 2x, 2 times pi over 2, pi. I have to get it in this format so I can see that even though it looked like a shift of pi, it's actually only a shift of pi over 2. That's a pretty tricky thing that we'll kind of investigate in the next chapter or the next section, but I do want to kind of show it now so it's not something crazy. All right, let's clear this stuff. So again, we can have all this stuff show up at once or some combination of them. And we're going to look at just one more kind of tricky example here that just has a lot of stuff going on. Whew, and boy, does it. Okay, so let's list it all. Let's list everything that we notice and kind of talk about where they're going. So first off, a value, it's negative, so there is a reflection. So there is a reflection. Got to keep that in mind. Amplitude is 5 over 2, which is 2.5, just to kind of keep that in mind. We can think about it either way. We have a cosine graph. That's important, but we'll deal with that more when we start actually graphing points. A B value here. Okay, we got a B value. That is actually going to affect our period, right? So period equals 2 pi over 3. Ooh, so that's our period, 2 pi over 3. That isn't even simplified. Interesting. We'll kind of see what happens with that. We also have a phase shift. So minus pi over 6, that is going to the right, pi over 6. Okay, and that's this value here, right? And we also have a vertical shift. We are going to be going down 2. So our midline is going to be going down 2. All right. Let's do this. Let's start off with the vertical stuff. So all the vertical stuff can kind of be thought of together. So amplitude, that sort of affects vertical motion, how high we're going up and how low we're going down, and the vertical shift. So kind of piecing these things together, a shift down of 2 means that we are going to have now a midline at -2. This is going to be our midline. Let me just draw this out. Midline, -2. That's our midline. That's where we're going to be oscillating around. And we are going to be going up 2.5 units from there and down 2.5 units from there. That is our amplitude. So -3, -4, -5. So this is -5. This will be 1. Okay, we're going up 2.5. So we're actually going to be going up to here and down to here. I'm going to make some lines there to sort of set my boundaries. Again, this gets a little messy, but I'm just going to do it just to keep this all in mind. As we're doing this, I wanted that to be this color. So that's our maximum at 1/2. Again, that's 2.5 units from the midline. And down here at negative 4.5, negative 4.5. That's 2.5 units below our midline. So that took care of a few things, right? That took care of thinking about amplitude and thinking about this shift. From here, we kind of got to think about all the x-axis values. And those are the ones that are tricky, let's be honest here. So what I'm going to do for myself is I'm going to set up a bit of a kind of rough draft up here. This is my x-axis. We know we're shifting to the right pi over 6. So let's just say that this is pi over 6. So this would be 2 pi over 6, 3 pi over 6. Oh, sorry, 3 pi over 6, which is, sorry, pi over 2. 3 pi over 6 pi over 2. 2 pi over 6 is, let's start this whole thing again. I'm sorry. All right, pi over 6, 1/6 pi. 2/6 is really a third, so pi over 3. 3/6 is 1/2, so pi over 2. 4/6 is 2/3, so 2/3 pi. 5/6, that one actually doesn't reduce. And 6/6, 6/6. Okay, so this is kind of a rough draft of scaling for myself. I know that my period is only 2 pi over 3. 2 pi over 3. Which in terms of sixths, because that's what this scaling is, right? This is 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. That's kind of hard to say. In terms of sixths of pi, this is 4 pi over 6. So my scaling needs to go 4/6 of pi from the starting point to have a full cycle. So we're going to be starting here. We're going to be ending after 4/6. So that's 1, 2, 3, 4. That's our ending point. Okay, this is great. Actually, this scaling here that we've kind of worked out slowly is just like perfect because this splits it up into 4 pieces. This is the middle. This is our 1/4. This is our 3/4 point. We've got everything we need here. This scaling in terms of sixths works great. So let's just go with it. So we have pi over 6. We have pi over 3, which was really 2/6. And we have pi over 2, which is, remember, 3/6. And then we have 4/6, or 2/3. And then we have 5/6. And then we have 6/6. I guess we didn't need this last one, but we're going to have it there anyway. That's our scaling. All right, let's think about what we're doing now. We've scaled the x-axis. We've scaled the y-axis. We have done everything basically. We're ready to start graphing points, right? So now we are graphing a cosine curve, a reflected cosine curve. So reflected cosine curve. Remember, reflected cosine curve. Instead of starting at the maximum, we're going to start at the minimum. We're going to end at the minimum because we're reflected. In the middle, we're going to have our maximum value. And then at these quarter points, we're going to have our midline values. Okay. So luckily for us, we already have our midline drawn. We have our line for our minimum. We have our line for our maximum. We can start putting stuff in the right place. So we are starting here on pi over 6, and we are ending over here at 5 pi over 6. So starting at minimum, ending at minimum. In the middle, At pi over 2, we are at our maximum. And then at the quarter points here and here, we are on our midline. And our midline is down here at -2. This had a lot going on to it, just an absolute ton of things that we had to keep track of. And I'll just be frank, this is like as hard as it can possibly get, really. Like I'm not holding anything back here. This is kind of what at the end of next week I'm expecting you to be able to do. I'm just throwing it all out there and kind of showing how these different things interplay with each other to sort of help this process out. But this is about as hard as it really gets. Let's go ahead and connect some points. If it gets any harder than this, we will just say, let's let Desmos graph it for us. So there is our graph. And in fact, let's do that. Let's actually examine a graph of this on Desmos here in a minute. But there you go. One cycle of it is graphed. I'm going to go ahead and clear my work, and we'll take a peek at this on Desmos just to kind of make sure it makes sense for us. And I'll talk about some things on there. Okay. So remember, Desmos defaults to radians, so we don't need to worry about that. Our equation was y equals -5/2 cosine of 3 parentheses x minus pi over 6, close parentheses, close bracket, -2. Oh, it doesn't love the brackets there. It wants me to use parentheses instead. That's fine. We will put parentheses around that. Okay, so here is our graph. Obviously, Desmos does not know anything about Desmos graphs way more than one cycle. There's tons of cycles here. And also the scaling is a little bit off. So our x-axis, we basically went from, we can type in numbers here in terms of pi. So let's just say we go from 0 to pi. And let's count by pi over 6. That's something that we did, right? We counted by pi over 6. And our y-axis, let's just make sure it counts by 1s for us. All right, so here we can sort of see things a little bit better, a little bit more kind of like what we showed here. We graphed ours from here, which was at -pi/6, to here at 5pi/6, with a maximum here at a 0.5 and at that place. So we graphed sort of this section right here. Let's even put our midline in there, y equals -2. Let's put that midline in there. I'll make it dashed. So we have that midline there at -2. And we could even restrict this. Let's just restrict this to pi over 6 is less than x. Sorry, is less than x, which is less than 5pi/6. So I'm even restricting this just so that we can kind of see just the section that we graphed here with our midline values, our maximum. It's not going to let us show the minimums because I didn't say or equal to. It doesn't really matter. It's not showing us these, but we can see they're at 5pi/6 in there. With all the work that we did, I knew how to restrict this domain and everything to appropriately show the one thing. But even if I don't, we can take a peek at the entire graph here and see just the section that we want, right? We can just kind of zoom in on the piece that is of interest to us if we were using this to solve a particular problem. We'll get more into using Desmos to help us graph these because obviously it's pretty powerful in the future. Anyway, good luck on the homework assignments, and I'll see you guys later.